Okay, so we talked about non-electrolyte solutes. What about electrolytes? Well, strong electrolytes are going to affect freezing point and boiling point more because they separate into ions and there's going to be more particles. So we have a little like correction factor here. It's called the Hoff Factor, and it has the symbol I. This is the ratio of particles in solution to moles of formula units dissolved. And you might think, well, that should be easy. But the actual Van 't Hoff factors are not the same as we might expect. Not because the ions don't dissociate, they do ionize completely, but then some of the ions effectively pair up in solution, and so then that causes them to not act as two particles, but as one. So here's an example of how you can get ion pairing. Each of these ions is solvated with water, but they can effectively pair up. And that's not something you can just predict by looking at a chemical formula or something. So what they've done is they've measured these factors. And here's a table for some ionic compounds. For sodium chloride, the expected factor is 2. You expect to get 2 ions for every mole of sodium chloride that is dissolved. The actual factor is pretty close, but it's 1.9. Magnesium chloride, we've got a magnesium ion and 2 chloride ions. So we would expect there to be 3 ions for every mole of magnesium chloride that is dissolved. The actual factor is 2.7. So the Van 't Hoff factor is generally going to be less than the expected, and you just look them up in a table. So when we have ionic solutions, we need to throw that Van 't Hoff factor into the calculation. So the freezing point depression is I, the Van 't Hoff factor, times the molality times the freezing point depression constant. Because for sodium chloride, you've actually got 1.9 ions for every molal of solution. And so that is going to increase the freezing point, right? Because there's multiple particles.
You would use the one in the chart and not the actual.
Which is the actual calculated one?
No, because you have the expected is the calculated one.
Oh, it is the ratio of particles in solution to moles of formula, but it doesn't end up being what we expect. So we would use the one from the table. Sorry, I didn't quite understand your question. And so for the boiling point and for the osmotic pressure, same equations, you just throw this factor in there. Because these are colligative properties, they depend on the number of particles. And when you have ions, you have more particles than the molality or the molarity would have you to think that you have. So, calculate the freezing point of an aqueous 0.1 molal iron chloride solution using a Van 't Hoff factor of 3.2. So the change in the freezing point is equal to I m delta T F. So we need the constant for water. Point what? 1.86, thank you. We used it once already, but it's long gone from my brain. 1.86. 1.86 degrees Celsius per molal. And so now the only difference is that we're going to throw in that Van 't Hoff factor, and then the molality, and then the constant 1.86 degrees Celsius per molal. And so delta TF 3.2 times 0.1 times 1.86 equals 0.5952. That would have 2 sig figs. So what's the freezing point then? But does the freezing point go up or down? It goes down because they go away from each other. Boiling point goes up, freezing point goes down. So we're going to take 0 minus that, and we're going to end up with our freezing point of minus 0. We'll actually round to 0.60. Any questions? If this was an exam question, the freezing point depression constant would be given to you. So the strong electrolytes are also going to have a bigger effect on the vapor pressure lowering. When you calculate with these strong electrolyte solutions, you have to account for the dissociation of the solute when you calculate your mole fractions. So let's do one of those. A solution contains 0.115 moles of water and an unknown number of moles of sodium chloride. The vapor pressure of the solution at 30 degrees Celsius is 25.7 torr. The vapor pressure of pure water at 30 degrees Celsius is 31.8 torr. Calculate the number of moles of sodium chloride in the solution. Well, which law are we going to use to calculate this? Which equation? Raoult's law, right? The vapor pressure of the solution was equal to the mole fraction of the solvent times the vapor pressure of the solvent. So we have both the vapor pressures, so we can calculate the mole fraction. So that's the mole fraction of water is going to be the pressure of the solution, 25.7 torr, divided by the pressure of the water itself. If you rearrange your equation incorrectly, you're going to end up with a mole fraction that's greater than 1, and that should alert you to a problem. So there's the mole fraction. It's asking us to find the number of moles of sodium chloride. That's the mole fraction of water. What does the mole fraction of water equal?
1 minus the
It's the number of moles of water divided by the moles of water plus the moles of sodium chloride. That's the definition of mole fraction, right? Do we know the moles of water? We do. So let's put those in here. 0.115 moles of water. And then down here, 0.115 moles. Can we solve for the number of moles of sodium chloride? We can. Now, just watch your algebra here. So we're going to multiply both sides by the denominator, essentially cross-multiplying. So I've got 0.80818 times the quantity, 0.115 plus, I'll just call it N, is equal to 0.115. So then, if I distribute that, I'm going to get 0.80818 times 0.115 plus n times 0.80818 is equal to 0.115. There's a reason that they tend to use nice whole numbers in algebra problems. It's easier to write them over and over again. So now I want to get n on the, I want to keep n on the left side, and so I'm going to take this part and subtract it from that. I'm going to move up to the top because I ran out of space, as usual. So n times 0.80818 is going to equal 0.115 minus 0.80818 times 0.115. And then I'm going to divide by this to get them, to get the n by itself. Isn't that lovely? 0.115 minus 0.80818 times 0.115. Press the equal sign and then divide by 0.80818 equals. N equals 0. This should have, oh, I gotta be careful. Well, I'll write it all out. 130795. Our sig figs could possibly be limited by this whole subtracting business here. Yeah, that would have uncertainty less than the third place. So we're going to be limited to, sorry, thinking out loud. I think we're just going to have two significant figures on this. 0.13 moles. Yeah, two sig figs. Any questions? You got a different number? Okay. Okay, let me check. Because I haven't screwed up nearly enough today. Oh wait, actually I have. Yes. Okay. Rewind. 0.27. With two sig figs, that's it right there. Moles. Questions? Number of moles of sodium chloride. Well, let's think about this. The vapor pressure depends on the number of particles, right? So this tells us the number of moles So this is telling us the number of moles of solute particles. That equals sodium ions and chlorine ions. but we're asked for moles of sodium chloride. So there's a factor of 2 involved here. Do we divide by 2 or multiply by 2? Got vote for each. Well, if we have, let's divide by 2. 0.014. We divide by 2, 0.014 moles. So 0.014 moles of sodium chloride would generate how many moles of ions? Twice as many, right? If we multiplied this by 2, then we get 0.054 moles. And if that was moles of sodium chloride, that would generate twice as many moles of ions. And so that's in the wrong direction. So this is the answer. This is the moles of solute particles. But the question's asking for moles of sodium chloride. I divided by 2 because this is telling us the moles of solute particles. If this was a non-electrolyte, this would be the answer. But when we dissolve 0.014 moles of sodium chloride in water, it makes this many moles of particles. Because each sodium chloride unit makes 2 particles, a sodium ion and a chloride ion. So when we're dealing with electrolytes, then you have to think about that. They did not give us a Van 't Hoff factor. If they gave us a Van 't Hoff factor, then we should probably stick that in there as well, but they didn't, so we'll just go with expected number. Any other questions?
What was that? Is squiggly X of water?
That's the mole fraction. Squiggly X is the Greek letter chi. Chi is mole fraction. So that's the moles of water over the moles of solution, which is solute plus solvent. Sodium chloride plus the water. Hmm?
How did you get that from the?
So we took this equation, the Raoult's law. The pressure of a solution is equal to the mole fraction of the solvent times the original standard vapor pressure of the solvent. And we know both of these pressures, so we rearranged the equation and solved for the mole fraction of water, the solvent. From the mole fraction, and thinking about what mole fraction means, then we calculated the moles of the solute. Those are the sorts of problems when you get through them successfully, you're like, cool, I did something. Some people think these are fun. Colligative properties and medical solutions. Again, solutions here not meaning answers to problems, but solutes dissolved in water. Osmotic pressure of solutions used in medicine is really, really important. Here's pictures of blood cells. This is what your blood cells are supposed to look like. They're not supposed to look like that or like this. Blood cells have semi-permeable membranes. And so if you're giving someone IV fluids, it's very important that the fluids you're pumping into them have the same solute concentration as what's inside the blood cells. Because you don't want osmosis happening on your blood cells. So hyperosmotic, another word they use is hypertonic, meaning it has a higher osmotic pressure than bodily fluids. It's a higher concentration, and that will draw water out of your blood cells and cause them to crenate, shrivel up, and get all pointy. Not good. Pardon me? That's what happened to the hot dog, yes. Yep. And this is what happens if it's hypoosmotic or hypotonic and the concentration is lower. Then the water will go in and they will swell and eventually burst, and bursting blood cells. Not good. So anytime they're giving you IV fluids, the base of that solution is going to be 0.9% sodium chloride, which is isotonic or isoosmotic with your plasma in your blood. These are pretty common units used in medicine: grams per 100 milliliters of solution, or 0.9% mass to volume. People use units that are convenient for them. Making solutions, they're not concerned with how many moles there are. They're not going to do calculations with moles. They could care less about moles. So if you're headed into medicine and you care less about moles, you just have to care enough to get through chemistry, and then you can forget about it. But a mass of sodium chloride in a volume of solution, that's easy to make in the lab. You weigh out the sodium chloride, you put it in a container, you add water till you get the volume, bang, done. There's no calculating or anything that you need to do. And 0.9% mass to volume, well, that is exactly the same thing, 0.9 grams per 100 milliliters, mass to volume.